Here's an example of using the law of cosines to calculate the angles when you know the sides of a triangle. So I've got three sides here, 5, 6, and 7. Let's call the angles A, B, and C. And I want to find the angles there. Now, in the previous example, we saw that once we had one angle and the three sides, it was pretty quick to use the law of sines to get one of the other angles. But I had to make sure that with that other angle, I wasn't doing the big angle. And actually, here, what I'm going to do is when using the law of cosines, I'm actually going to do the big angle first, and then I know that I don't have to worry about it with the law of sines later. The thing is, the law of cosines will get it right. Sines have an issue of an angle in the first quadrant here has the same sign as an angle in the second quadrant. So the y over r is the same here as the y over r there. And that gives a problem that the law of sines can't distinguish between this one and that one. And so when your calculator, when you say give me the inverse sine, it's always going to give you the small one. Cosine, on the other hand, doesn't have that problem. In the first quadrants, the cosines are x over r, and well, in the second quadrant it's also x over r, but the x's are negative in the second quadrant. So if the angle needs to be in the second quadrant, the cosine is going to turn out to be a negative number. And your calculator is going to be able to handle that. The inverse cosine button on your calculator will give you both first and second quadrant angles depending on whether the cosine the number you put in, is it positive or is it negative. If you put in a negative number and say give me the inverse cosine, it's going to give you an angle in the second quadrant. Okay, so knowing that, I'm going to use the law of cosines. I can use it on any angle. In fact, I could do it on every angle if I want, but it's usually easier for me to use the law of sines. To make sure I get the law of sines right, I'm going to use the law of cosines on the big angle. I know my handwriting is a little sloppy here, but I said it out loud. Use the law of cosines on the big angle. Right? So the biggest angle is the one across from the biggest side. The 7 is the biggest side. Angle B is the only one possible that could be bigger than 90 degrees. The law of sines will get the other two angles right. I'll use the law of cosines to get the big one here. So the law of cosines says the side opposite of B here, 7 squared, is equal to the sum of those two squared, 5 squared plus 6 squared, minus 2 times 5 times 6, all times the cosine of angle B. So I know all those side lengths, I just don't know the angle. Well, I can solve for them. I'm going to take some stuff over. I got a 49 over here. That's the 7 squared. And I'm going to subtract 25. That's the 5 squared. And I'm going to subtract 36, right? And that's going to be equal to, what's this, 60? So I've got a negative 60 over cosine B. Right? So 49 minus 25 minus 36. All of a sudden I'm feeling lazy, so I'm going to do it in my calculator. 49 minus 25 minus 36. So the stuff on that side is negative 12. And this is negative 60 cos B. So when I divide both sides by negative 60, this is positive 12 over 60 equals cosine B. Now there's probably something I can simplify, but it doesn't really matter. Point here is that this stuff, when I subtracted, came out to be negative. That was already negative. When I divide, I'm positive. So cosine of B is this positive number. I'm going to end up with a first quadrant angle. And so it really didn't matter. However, if this had come out to be positive when you divide by that negative 60, then this would be negative, and B would be that second quadrant angle. So anyway, B is the cosine inverse of 12 over 60. And so I let my calculator do that thinking for me. Cosine inverse of 12 divided by 60. Yay, yay, yay. And I get 78.46 degrees, something like that. Okay. Now, my calculator still has that to several more decimal places, so I'm going to let it keep that in my next calculation. Right? Now that I know angle B here is this 78.46, I'm going to use that to get one of these other two angles. Right? Having already been careful and calculated the big angle with the law of cosines, I know that A and C are less than 90 degrees, and therefore it doesn't matter. The law of sines is going to get it right for me. Maybe to be a little careful, if I'm still feeling a little insecure, use the law of sines on the smallest one. 5 is smaller than 6, so angle C, which is across from 5, will be smaller than angle A, that's across from the 6. So let's do angle C next, just to be careful. The sine of angle C divided by its opposite side, 5, equals the sine of angle B, this angle right here, 78.46, divided by its opposite side, 7. And I can find angle C. Sine of C is 5 times the sine of 78.46 divided by 7. And so here we go. I'm going to say, tell my calculator, 5 times the sine of the previous answer divided by 7. And so I get the sine of C is 0.69985, whatever. And so C is going to be the inverse sine of that. Again, I'm not rounding that. I'm letting my calculator remember as many decimal places as it can. I don't know if I've emphasized that enough. I get tired of people rounding part way in the middle of a problem, and then it just makes the answer by the time you get to the end really way off. So, so now I'm looking at the sine inverse of the previous answer, and I get 44.4 degrees. All right, 0.415, so close enough. And now that I have angle C and I have angle B, I can get angle A, because angle A is going to be 180 degrees minus both of those two, 78.46 minus 44.4, and whatever that is, 180 minus 78.46 minus 44.415. Anyway, it looks like about 57.14. Right. Again, the number of decimal places that you need at the end here depends on the application of what you're doing, but the way you calculate it is get one of the angles with the law of cosines, preferably the big one, because then you don't have to worry later. Get the big angle with the law of cosines, you can then come back and get one of the smaller angles with the law of sines, and then just subtract to get the third angle. Okay. Anyway, there's a second example. I want to do one more thing here for you. Sometimes, one more example. What if I had this triangle here? What if I said 3, 4, 9, right? Something like that. Now, some people look at that and can see right away that there isn't any way this is going to work, because 3 and 4 only add up to 7, and how the heck could they stretch to be 9? Well, maybe you don't recognize that, but watch what happens when I try to solve for angle B here. Again, 9's the big side, so I'm going to try out for angle B. I say that 9 squared equals 3 squared plus 4 squared minus 2 times 3 times 4 times the cosine of angle B, right? 9 and B, okay. So I've got 81 minus 9 minus 16 equals negative, what's this, 6 times 4 is 24. That's cosine B. So the 81 minus 9 minus 16, that's 80 minus 15, 65, 65, 60, 54. So 54 equals negative 24 cosine B. Dividing both sides by 24, you got 54 divided by negative 24 equals cosine B, and all of a sudden we got a problem, because 54 divided by 24 is 2.25. There is no angle whose cosine is like that. Cosine is always between minus 1 and plus 1. So there's no triangle that'll fit this condition. Okay, so that's one thing that comes up. Just keep that in mind. that if you've got a triangle that really doesn't work, something's going to go wrong. You're going to end up with some calculation. If I tried this in my calculator and said cosine inverse of negative 2.25, my calculator would say error, domain. Right? I tried to plug a number into the inverse cosine function that it doesn't know how to handle. Right? Anyway, there's a couple examples of the law of cosine.